Right, end of the day, I can see people are getting a bit, I get getting a bit tired of all the information they have received. And to be honest, I'm up against a few very interesting different talks. So welcome for being here. And this is me, sometime in the 1990s. I used to be quite a cyclist back then. Then university happened. But my love for cycling was inspired by my family, mainly by my dad, who liked cycling so much that he became an official for the KNWU, the Koninklijke Nederlandse Wielrenunie, the Cyclists Union. Fast forward 20 years, and Luminis is building a software system for this KNWU. And this talk is all about that system. It's all about the things we learned, the things we did right, the things we did wrong. This is a case study. This is a slightly different story than the things you have seen up to now today. And this is not an idealized story. There will be gaps in it. There will be points where I say, okay, we screwed this up, but we know how to do it better. Little bit about me. I'm Angelo van der Sijpt. I'm a fellow and software architect at Luminis Arnhem, where I deal mainly with security and connected devices. As I told you, I used to do a lot of cycling. Nowadays, I'm more into running, obstacle course racing, and my Saturday mornings are spent doing Krav Maga. So no cycling anymore. I still keep busy. This talk will be organized as a race. And because cycling is a reasonable sport, I start counting at 0. I'll tell you a little bit about the project. Then we go into the details of cycling that you need to know to appreciate the rest of the talk. And the two main stages are about calculating results. How do we get from the input we get to a race result? And finally, how do we present all this stuff to our user? So starting with the project and all the way through to presenting the stuff to our user. Along the way, in the second and third stages, we have some sprints, some key takeaways, and I will point those out. And if you take away anything from this talk, take away the takeaways. Let's start with stage 0, the project. KNWU, the Dutch Cyclist Union, is the purveyor of all things competitive cycling in the Netherlands. They have about 30,000 members, which are holders of racing licenses, and just about all racing events are not necessarily organized, but overseen by the KNWU. And we were lucky enough to do a project for them, the KNWU RaceDirector. We'll go into the details. Project was not a big project. We're talking about summer 2013. We spent about 8 weeks building the initial stage with just about this team. And since that, every year we have spent 80, 120, 160 hours, something like that, in maintenance because the rules change, cycling rules change, and requirements change. So about those requirements, what are we trying to do? We want to automate the classification of a race. The classification is a list of results that we end up with at the end of the race. And we want to do that after the race, but also during the race. We want to have an idea of what is going on the track during the race. Our scope is everything from the moment we have a start list, a list that says these riders with these names and these numbers will be participating, up to uploading our results to the KNWU website. And a slightly more interesting requirement is we want to have a desktop application. You'll see we have we'll have a link to some hardware. We might be in a location where there is no internet. And for first and foremost, there is a group of users who are just used to having a desktop application. So miniature stage, what we call a prologue about the project. Next up, a little bit about cycling. We don't only have the KNWU, we also have the UCI, the Union Cycliste Internationale, is a Swiss organization that oversees all things competitive cycling worldwide. And as these institutions want to do, they create regulations. They have regulations that state what a bike looks like. There has to be a triangle shape in there somewhere. There is a regulation that says you should not have an electric motor in your bike. Sounds like a reasonable regulation to me. There are also regulations about the types of races that can be held with the rules that go with it. And the type of race we're mainly interested now is the so-called criterium. The criterium is one of the most common types of races in the Netherlands, which is the proverbial rondje rond de kerk. The basic rules are very simple. We have a small circuit, we have individual competitors, and whoever finishes the race over a set number of laps first wins. Well, almost. Of course, we have all these regulations for a reason. Main reasons for having these regulations is for keeping the sport safe and competitive. As an example of keeping the sport safe, each time a group of riders is about to be lapped by leaders in the race, it is possible to classify them beforehand, so they can leave the track and keep the track empty and safe for the rest of the riders. This is a process known as elimination. We can eliminate a rider before, but it does not mean he is disqualified, he is kicked out of the race. No, he is classified just as if he would have finished the race, he just can stop a few rounds earlier. Another rule is that whenever a mishap happens, say you get a flat tire, and you are on a short circuit, it is possible for you to get 1 lap, sometimes 2 laps of compensation. You have the time to repair whatever happened, and when the group that you were in comes by again, you can just tag along. So first rule keeps things safe. Second rule, known as compensation, keeps things competitive. You don't want to disqualify anyone just for having a flat tire. And there are regulations about what a list of results looks like. And we used to create these lists by just looking out the window and writing down whatever we saw happening on the road. And a serious part of the KNWU curriculum for officials was about good techniques for writing down numbers. Then later on we moved to using consumer-grade cameras for photo finish. There were professional photo finish devices back then, and they are digital now. They used to be analog back then. A video camera can do roughly the same thing. And nowadays we moved to chip-based systems. Each bike has a chip on it. This is a MyLabs Champion chip, which is an active transponder chip. And on the finish line, there is a loop. This loop is connected to a decoder. And it's the task of this decoder to interrogate each chip that comes by and send the results of this interrogation to an operator PC. By default, this decoder is ships with software which is intended for car racing. And car racing is just slightly different than bicycle racing. For instance, there is no elimination rule, there is no compensation rule. Our system will be running on this operator PC. That is the thing we will be focusing on. So that tells you enough about cycling. Now, moving on to calculating results. You remember the requirement that we want to automate classification, both during the race and after the race. So how do we get from this, a chip, all the way to a classification? In a schematic sense, system looks a little bit like this. We have chip events. We see these chips coming by. We have operator actions. Someone presses the start button. And we have some base information, such as which race is going on at the moment and what riders are currently in the race. We drop all of this information into a black box and end up with a situation. Starting with the chip events, this is what comes out of the decoder. The decoder sends UDP packets which contain a protocol number, a number of flags that tell you how to interpret this, and there are a number of there's a type of record in this. And the O1 tells us that this is the record that says that a chip has passed. So we can get rid of this header. We know that the rest of this data consists of records. First up, we have the type of field, which tells us what information is in this record, and we have a length. When we parse this data using that same information, we can make this into separate records. So we had a column for types, we had a column for length, and there is a terminator on the packet. We know that OA is the chip ID. And in this case, we have chip ID XX and 5 nines. All chip IDs have the same pattern, 2 letters and 5 numbers. We have a time in here, and this timestamp is an absolute timestamp. You can assume that the decoder has a very accurate clock. And in fact, in events where multiple decoders are used, these are synchronized to a GPS receiver, which is plenty accurate. And there's some more information in here, such as having your battery status. The chip does not have a display, it does not have LEDs or buttons, so you need to know whether the battery is running low in some way. So now we have our chips, and we've seen that we have time in there. And of course, time is an interesting component in this type of race. However, time is always hard to reason about in any system. In fact, I know of only one case in which time is a reasonable component of your algorithm. If you're mystified about why this works, Google Sleep Sort. Trust me, it's the only case in which you want time to be a part of your algorithm. In all other cases, sprint one, abstract away from it. First, not necessarily the first thing we learned. It was one of the first things we started practicing. You have seen that pack of rules, and the rules together make a system of rules. What you then can try to do is to separate it into smaller components. And the good thing is, for these types of rules, this works pretty well. So how do we get from a chip event to a situation, a temporary classification? Well, we have a chip event. We can make that into a chip passage. We know that the chip has passed. And when we mix in some event and rider information, we can make this into a rider passage. We mix in some time, and we can make ourselves a race time out of this. We can aggregate a number of those to end up with rider labs. We can calculate the position of a rider within a lab, also by mixing in this compensation rule. We can find out whether this was an exceptional lab. We may have missed a chip passage, so it looks like the rider has taken twice as long to finish this lab. We can start making groups, and I won't go into why groups are interesting for labs, but trust me, they are. Then we can make a set of labs within a race, and this ends up at a situation. Main thing we took away here is divide and conquer. No matter how complicated the rules in our case were, they are deterministic, and we can separate them. And we're going to use that later on. Those rules are well and nice, but we don't only want to generate a nice picture from it, we also want to reason about it in an automated fashion. And we take some inspiration from the early 1980s. And in the early 1980s, I looked a little bit like this, and my vocabulary was a lot more limited than it was today. President Reagan was about to sign the Strategic Defense Initiative. This was somehow considered a respectable hairdo. The NES was just about to be the hottest thing for Christmas, and MTV actually broadcast music. Those 1980s. And those 1980s also brought us the second wave of AI. The first wave of AI, as Mark Rendell earlier alluded to, consisted of trying to program the intelligence of an expert into a system. This is what brought us things like Lisp. Second wave of AI tried to separate two things. It tried to separate reasoning, which we put into an inference engine, and knowledge, which you put into a database. So on the left we have a user. The user asks a question to the system. System starts reasoning with the rules it has, in the database about this problem, and returns a result. And the nice thing is, if the system cannot answer the question, we go back to the expert, and the expert can start inputting new information into the database. So we don't have all knowledge locked in our algorithm, we have a separate mechanism. This worked pretty well in the early 80s, but pretty soon what is known as the second AI winter came. First AI winter was when we were a bit disillusioned that we couldn't build relational therapists in Lisp. Second AI winter came about when it turned out that expert systems, we still use expert systems in many different cases. Most recommendation systems are structured like an expert system. But expert systems turned out to be quite limited in what they could do. Still, we can draw some inspiration from this. And the system we will be drawing inspiration from is a system known as Hearsay. Hearsay was a system that was intended to let you talk to your computer as you would in Star Trek. And one of the main components of this was recognizing what a user was saying. And they used a layered approach for this. So let's say we have some waveform. First we have an agent that tries to split up this waveform into phonemes. And a second layer, a second agent, tries to take these phonemes together, make them into pieces of words, or maybe even in longer words. And the third level tried to make it into words. Well, this is a highly simplified form. In practice, it was a little bit more difficult because speech understanding is not a deterministic process. For instance, there was a lot of feedback in here. When a higher level determined that is not a word, it fed this back to the lower levels, which then could reassess their determination that a certain waveform represented a certain phoneme. System was structured on the Blackboard pattern. And the Blackboard paradigm says we have a bunch of agents. And agents are experts. They are very good at one thing. And they sit together around a shared blackboard. And on this blackboard we put information. And each agent can go up to the blackboard, say, okay, I recognize this, combine this into new information and post this on the blackboard. And in Hearsay, this also had a confidence level. And because all those agents need to talk to the blackboard together, we also had quite a bit of scheduling in here. Do we do speech recognition like this nowadays? Well, no. Things like Siri are mainly based on Markov chains, which is a simpler and more reliable and better learnable mechanism. Again, as I said, there's no reason we cannot try to apply this. This works because our system is more deterministic. Let's say we have a blackboard and we have a bunch of agents, and we start dropping information onto our blackboard. Some riders combined with their chip numbers. We post this on the blackboard as information for all to see. We post the information that the race has started to the blackboard, and then we add a chip event. Some chip has passed at some time at some moment in time, in wall clock time. We post this on the blackboard, and this can be the trigger for one of the agents to take this information together with the list of riders and make this into the information that a given rider has passed the finish line. Put this back on the blackboard. And a second agent can start using this information, so this secondary layer of information, combine this with some other information. I know when the race has started, so I can tell you what the race time of this rider is. Put this back on the blackboard. And we can not only stack information of chip events on top of each other, we can also start aggregating information. So an agent can take this event, this passage, and combine it with information he has been keeping track of before, such as all the riders in this lab. Update this information, post it back to the blackboard. So what we see is that a simplified form of Blackboard works well when you have complex but divisible rules. When we have layered interpretation, the influence only goes in one direction and never goes back. And it allows you to have a reproducible state because we have a deterministic set of rules. So we can now start simplifying this a little bit. Agents, check, we will need those. A Blackboard, well, no, we don't need a centralized repository. We can just ask agents to keep state. They're all running on the same system anyway. We had only one operator PC in the diagram. Scheduling, well, no, we can rely on events. And the system then looks a little bit like this. We have our agents sitting around within the black box. We put some base data in this, so the rider information. We put primary events in this, and primary events are those that cannot be denied. A chip has passed the finish line, sure, we cannot argue about it. The operator has pressed a button, we cannot argue about that. The secondary events are all the things that you on the previous slide saw in black, the interpretation events. The reason we separate those is that it keeps most of your state immutable, which keeps your system a lot simpler. If I, for instance, were to change my base data, add a write or change a name, I would have to follow the impact of this information throughout the system. We don't want to do that, that sounds like work. What we instead do is we throw away all the secondary information, change the base data, and recalculate the state of the system based on this new information. This realization has made our system and mainly our persistence of events a lot easier. We don't always need to store all state. We only store the state that is absolutely necessary to recalculate your state. Moving down to some code. This part of the system is built on OSGi, and I like to use the following notation for this. The block in the middle is a component, which is a Java class. Then the thing on the top is a provided service, and a service is identified by its interface, which is just a Java interface, which can have a bunch of properties. And on the bottom end, we have dependencies. Components depend on a service of a given type, so we can connect the connector on the bottom to the connector on the top from another system. Basis of the system is this. We have an event bus. All agents can post events to this event bus, and all agents register themselves as being interested in some type of event. We don't have a nice event syntax for this, we just use Java classes for this. For instance, we have a new race around event here. And for each type of event, we have a handler. So each agent is registered as both an agent and a handler for a number of events. As such, this is what you would call a purely functional system. Mark Randall just called Algol a functional system. You cannot get information in or out. The same thing goes on here. First up, we want to get information in, so we add some persistence. We get an event store, and the event store posts all the events that come into the event store to the event bus, and it stores them. What can we do? We can send a new event, and we have an update mechanism. Sometimes we have reasons to delete events or to move events around in time. And the rest of the mumbo jumbo in this interface is to do this in a type safe or in a thread safe way. Furthermore, we have some base information, so the participants' information, for instance, and agents can talk to each other. This is identical to the image I showed you before. This is how we can calculate state. Now there is one special case, and that is updating information. We'll see later that there is a command to add a rider to the race. And that means that we have seen some chip, which was not known at the moment. We add a name to it. We update the base data for this. We update the list of participants. We reset the event store, the event bus, which means that all secondary state is thrown away, and we instruct the event store to replay all of its events. That's the basic mechanism. Zooming in, what types of events do we have? Well, we have a group added event. Some agent has detected that something called a group should be added. And a race rounds agent reacts to this event. And you see that in the end it sends a so-called new race round event. Of course, I picked this code because it's nice and concise. Most of the code isn't that much more complicated. Most of the agents, and we have some 19 agents and about 50 different types of events. Each agent reacts to about 3, maybe 4 types of events and sends 1 or 2 types of events. So our divide and conquer mechanism worked pretty well in the end. Now you should be wondering, isn't this event sourcing? We are taking events, we are processing them, we are calculating state. We're not storing state, but we're only storing events. It's pretty close. I think the main difference here is that we allow those so-called secondary events and we always throw them away. I'd say that tells you enough about calculating results. We learned that we should abstract away from time. You don't want time in your algorithms, no matter how prominent it features in your domain. If possible, you want to split up rule sets in smaller components, and when you have done that, you can use a Blackboard pattern to calculate state using all these nice and complicated rules. And finally, once you realize that not all events are equal, your life gets a whole lot easier. So that sums up calculating results. Now we need to get all of this information to the user somehow. And we had this interesting requirement that said we need a desktop application. Given the context I've given you, this seems more obvious now. We may be in a location where we don't have a good internet connection. We have a link to hardware. We have this decoder sitting there. And whenever you're working with hardware, you want a solid feel of an application, whatever that may mean. We'll get back to that. From a high level, application looks roughly like this. We start with a decoder on the left, which talks to a Java OSGi based backend. And our front end is built entirely on web technology. Angular, HTML, and we have desktopified it. First obvious question, why web technology? We have a number of reasons for this. This is an early mockup. And main thing you notice here is that it has a high information density. We have lots of text everywhere. There are lists and there are lists within lists. And that even gets worse once we get to the more detailed designs. Then we even have separation within lists. So it's all lists, lists, and lists. I happen to know a technology which is really good at doing the same thing over and over. And HTML is just really suitable for showing lists of lists within lists. Second part. We have some future plans. We could have built a system like this. Make it one monolith, it's running on your own system anyway. It was pretty clear that we have reasons to separate the front end and our back end a little bit better. For instance, we might want to add a secondary display to the system which shows simplified information. You saw on the previous slide that we have a high information density. When we want to get that down a bit and present it to other users, we can just as well use a separate system for that. We could start publishing this information to the internet. How great would it be as a cycling enthusiast that you can see all the information, everything that's happening live based on those chips on your own phone when you're sitting there next to the track. And finally, I mentioned that this is not a big project. Every year we have a few man weeks of maintenance. So what desktop technology do we pick? The blue line is JavaFX. Well, it's sort of up and coming. The green line is Swing. That's not up and coming, it's down and going, let's say. But web technologies are much more available. This is just based on the number of Stack Overflow questions, which is a reasonable indication of the interest in the market in a given technology. This also means that web application developers are way more available than specialized desktop developers. This is another reason. So we have decided that we want to use web technology. Sun has been referenced in a number of talks today. And it was Bert this morning that said Sun had to pay off the network is the computer. And they had a good reason for that. They built mainly networking equipment, so makes sense that they should say that. And we've also seen this man, or at least this man's work in this morning's talk. This is Peter Deutsch, the same guy of Deutsch's 8 fallacies. And each of these fallacies applies to distributed systems. And Deutsch said when when you make these assumptions, when you make the assumption that the network is always reliable, and you build your network on that assumption, in the end, you'll be screwed. Now we're running on the same system. So maybe we don't really care. But let's take a few. The network is reliable. Well, it's on your system. Latency is 0. It's not 0, but it's close enough. Bandwidth is infinite. Close enough to infinite. Transport cost is 0. There is no transport cost. Most web frameworks we work with nowadays are built on these fallacies. I have not seen any CQRS talks today, but all of those start with remember the fallacies and this is how we solved it. That means that we get error handling in our application. Maybe our call doesn't go through. We need some progress indication because things might take a long time. We want to store local information and we get nice APIs like local storage. These things make your system more complicated. If we can leave all of this out, we end up with a more manageable system. As I said, it's not a big system. We have about 35,000 lines of Java code, which is not a lot at all. We have only 10,000 lines of JavaScript code. So somehow leaving out all this optimization makes your life simpler. First takeaway, forget about Dodge. Second part, I already alluded to CQRS. Who knows CQRS? 1, 2, 3. Close enough. I'll give a short introduction then. CQRS stands for Command Query Responsibility Segregation. And the idea is that the pipeline through which commands flow is a different one than the pipeline through which queries flow. So it's a bit like an MVC pattern, but distributed over the network. A client can send a command, change this to a domain. The domain is the main storage. And when something changes in the domain for whatever reason, based on something in the command, it sends an event to a read model. And a read model is the state which will be used for answering queries. So a query comes down and a data transfer object goes back up. Because a read model is immutable, we can always replicate it. That does mean that we may be looking at older information, but we take that part for granted. Because we're running on the same system, we can add one component, which is notifications. We can tell the UI that something in the system has changed. Technology-wise, well, it's not all that complicated. We have some notifications. We just use HTTP long polling for this. We could have used WebSockets or anything else. We built a long polling system and it works fine. The query and command part is just HTTP. HTTP gets, HTTP posts. And we tie that to our nice backend we had by adding an endpoint. Commands and queries come into the endpoint. Queries are translated into actions, into questions asked from the agents. And all the commands are commands that go directly into the event bus. And the other way around, agents know when their state has changed because there is no centralized Blackboard. Each agent keeps track of its own information and it knows when its information has changed in an interesting way. So that's a reason for information to go up, for notifications to go up. As an example of a data transfer object, this object represents a single race. A race has some base information, it has a date and a time and a category. And we have a bunch of commands and a bunch of queries in here. And because those commands and queries are separated, it turns out that Blackboard and CQRS work together pretty well. Cyclists tend to travel in packs. And when you get a herd like this thundering over your finish line, you can count on about 50, up to 50 chip events a second. We had a lot of secondary events, so there's a lot going on in the system when all these chips are being processed. As it turns out, for the backend, this is no problem at all. Even recalculating all the state, that is not a serious problem. There's no considerable time that goes into this. However, your front end will turn out to be a bottleneck in this. What we built for this is some filtering. Not all events go to the front end, and especially duplicated events. Hey, this list has changed because one rider has been added. Hey, this list has changed again because another rider has been added. Those get deduplicated. So even though the network isn't the problem anymore, your DOM will likely be your new bottleneck because you're using it in a very different way than you would if it were a regular JavaScript application. You're asking a lot more from it. Who knows the term HateOS? Okay, better than CQRS. Good. HateOS, hypertext as the engine of application state, is one of those mechanisms that helps you get the complexity of your web application down. This image is the Richardson maturity model, which says that on the lower level we use HTTP invocation, use it like it is a remote procedure call. On the level above it, we at least put our resources on reasonable URLs. Level above that, we use HTTP verbs and we use HTTP status codes. And in the top level, we use what is called hypermedia controls. And those hypermedia controls are, they mean that the user, the client should never have to build its own URLs. Do we have any front-enders in here? 1, 2, 3, 4. Okay. Those 4 guys, go buy them a beer later, because those are the guys that take our crappy REST APIs, which we built to be small and elegant, and make it into a working web application. And one of the things they do is they build URLs. They take some server name, then they put in some identifier they got from somewhere else, put a slash in between. Those are the things you don't want them to do. There is a lot of information that gets moved into the front end in that way. So we use the same mechanism here. This is the same data transfer object we saw earlier. And we have an add rider command here. This add rider command says I have some chip which I don't recognize and I add a name to it. That's basically it. The code we get when using this mechanism looks a bit like this. Most of it is plumbing and error handling. We can't get around that for some reason. But notice line 4, the URL part. Apparently, this is Angular. We have some current race service. We ask it for the race. We ask that for its commands. And we ask that for the add rider action. And we post our information to that action. It turns out, using this is another mechanism to make your code a lot less complicated. Remember those 10,000 lines of JavaScript code I mentioned earlier? Well, that included testing code. When we strip out all the testing code, we're down to just 3,000 lines of JavaScript. Because we don't have to do all the optimizations, and because we give the front end all the information it needs when it wants to present something or when it wants to undertake an action. Usually you don't want to go overboard with this. You don't want to make you don't want to use very large payloads. You don't want to have a huge load of fine-grained queries. Not only because that doesn't look good in the front end, but mainly for performance reasons. Most browsers can download 6 files simultaneously. And when you want to do 50 calls to build up one page, that will lead to a noticeable performance degradation. Because we're on the same system, don't bother. This is what my desktop looked like a few days ago. What makes a desktop application into a desktop application? Well, it has a menu, and it has a window which doesn't have an address bar. And I have installed it on my system, and there's an icon somewhere. But mainly, it's the way it behaves. This is a piece of my Facebook feed, and you can select text. It feels like a document. And those, it turns out, those are the most annoying things in a desktop application that is actually a web application. Weird text selection that makes you feel that the application is a document, gives you a less solid feel. And scrolling effects. When you scroll down in a text field and your whole page bumps up, that makes it feel like a less solid application. And as it turns out, you can fix that pretty easily. Those text selections, though, that's a bunch of CSS rules. You can stop the weird scrolling effect with a few lines of JavaScript. It doesn't take much to make the application feel like a desktop application, feel like a more solid application. In our current system, we launch our application like this. We assume that Chrome is available on your system, and in line 4 it says here --app, which means we start Chrome in app mode, which is intended for kiosks and these kinds of applications. Does it work? Well, it works pretty well, actually. We have the top window is a swing window, which shows you that the Java process is running, because we still have a separate Java process and a separate browser process. And the bottom half is the RaceDirector window, which actually is a browser, but it doesn't really feel like a browser. Are our users happy with this? Well, reasonably. We still in that front end, we have some performance issues, and there are some places where the webbiness shines through. For instance, we have that importeer button up there. That allows you to import a file. Then you get an ugly browserified file dialog. You perhaps want to drag files into it. We can do all of that in JavaScript. It will never look as solid as a desktop application. Another part is printing. Printing information. We fix that by using hidden iframes. That's not the ideal way, but it's another thing where the webbiness of this thing, the document base of this thing, shines through. If we were to do this over, I'd pick Atom's Electron. Electron is a framework from the guys at GitHub, and it allows you to package your application in a process that feels more like a desktop application. On the top side, we have a rendering process, which is basically a browser which contains your own JavaScript, HTML, CSS. It contains some desktop integration, which are JavaScript APIs for creating menus and the like. We have some inter-process communication code, and the main process is just a Node.js process. So you can interact with the file system and do all the other things that Node.js does for you. And a basic Electron application consists of a package file, which tells Electron what this application is all about, a main application, which is the thing which gets started, and in this case we just start a window and let the window contain our index file. That's the basic mechanism which you use to build an Electron application, and we have some mechanisms for inter-process communication, either asynchronous or synchronous. We can send information both ways. Does this work? Well, it works a little bit better. We have been building a prototype for this, and it turns out it's not all that hard. We can package all this Java process we had into our Node.js process, and we end up with an application that is one application, can be installed, feels solid enough, and it gets pretty close to being a desktop application. Still, it feels a bit weird to use web technology for building a desktop-based system. Good thing is, we're not alone. Anyone heard of Vivaldi yet? A few? Vivaldi is a new browser by some of the guys that built Opera back in the days. And Vivaldi is totally built on web technology. We have Atom, the editor from the guys at GitHub, totally built on web technology. We have Brackets, which is a front-end centric editor by Adobe, totally built on web technology. So what we see is that web to desktop technologies, they are slowly coming online. However, I wouldn't go all in yet. There are a number of frameworks around, there are a number of approaches around. You cannot be sure that any of these technologies will stick around. Yes, GitHub is a pretty reliable company, but there is always a chance that they decide it's not in their strategic interest to keep supporting this. So, same goes for all the other applications. In fact, at the moment, maybe this is different in 5 years' time, but at the moment I would treat this like it were JavaScript a few years ago. Assume your application is a web application and it uses all the rules of a web application except for it being local. And use the desktop technology as a way to make the application more convenient for your user. So just as we did with JavaScript, your application should be able to work well without it, but your life gets a lot nicer when you do include this technology. That way you make it easier for yourself to switch over from one technology to another. I think tools for building web applications will be pretty stable. These tools, I see some change in there. However, this web technology comes with its own perils. About 2 weeks ago, the news story broke that the Messages application, which used to be called iMessage on the Mac, actually runs a browser. It shows all your nice chat bubbles using a web view. And researchers found out that by sending a specific line of JavaScript to it, you can amend to the browser running on your to the browser context running on your system. And what they did with this is they appended some of their own JavaScript code and were able to dump your entire messages database to their server. iMessage is incredibly secure, but not this part. And this is something to be aware of. On the web, we are used to living in a dangerous environment. Browsers are sandboxed. You cannot touch the file system. Browsers have all kinds of rules to prevent cookie stealing, to prevent cross-site requests. And we have all this. For the web. We don't have this for desktop yet. Remember that essentially you're running a browser which has, through this main process, unfettered access to your system. I'm not trying to scare you here, but maybe I am. That sums up the presenting and interaction part. So what have we seen? We don't need to care about Deutsches fallacies all that much. They serve their purpose in a real web situation. When you're running on your own system, you can turn all the knobs to 11. CQRS works pretty well when you have this command pattern that a Blackboard uses. Your new bottleneck is DOM updates, but as soon as you have some optimization there, some event deduplication, you'll find out that using 8OS makes your application a lot less complicated. It doesn't take much to make your application feel like a desktop application, and you can make this even a little bit nicer by including some of the new web to desktop technologies that are slowly coming online. So that sums it up. As I promised, it's a story of the project as we did it, and it's a bit of a messy story. It contains a lot of loose ends, but then again, that is the way these projects go. Do we have any questions at this moment? We have a few minutes left. Go ahead.
You mentioned the chips, you use UDP. Do they send multiple messages every time they come close to a reader, or do they only send one message?
The question is, these chips, when they are detected, they generate a UDP message. Is it possible that for one chip message we get multiple of these events? That's your question, right?
The question is, does it send multiple? Because you don't have a confirmation that the message is...
No, it does not send multiple messages. It's the task of the decoder to determine when a chip has passed, and then to send only one event. So we can rely on the decoder there. In practice, it will send about 50 pulses between the loop and the chip. But it's the task of the decoder to make sure that it somehow calculates the moment that the chip was over the finish line and only counts that moment. Any other questions? Go ahead.
Why did you specifically pick Angular for front-end?
Question is, why did we specifically pick Angular for front-end technology? There are a number of reasons for that. The main reason is the type of data we are trying to show. It's, as I said, it's all lists, with a bit of styling on top. And Angular's scope mechanism and its bidirectional binding, we only use one direction by the way, but its bidirectional binding help us in reducing complexity of the front end. That's one reason. Another reason is that within Luminis we are starting to standardize on one web development stack for most projects, which includes Angular and which in most cases includes TypeScript. We did not use TypeScript in this project, we did use Angular. Does that answer your question?
Yeah, but the Sprint 3 is, well, that's why you have this bottleneck, because if you try to render a lot of lists with Angular, at some point it just stucks. It's like something about 1,000 data binded elements on your page, and because of its mechanisms, it just cannot work properly.
Yeah, you notice that that Angular's data binding mechanism does not work well when using lots of data bindings. Yeah, that is true, and we do use some optimization for that. For instance, we only render the part of information that you're actually looking at to reduce this amount of information. Furthermore, we don't use. We started out using watches for updating our UI. Turns out that doesn't work out all that well. But scope updates work reasonably well, and with the deduplication that we do in the backend, it works reasonably well. Still, you need a rather beefy PC to handle all these updates. That is true. Have I answered your question with this? Okay. Final question? All right, then I will not stand between you and the bottle. Thanks.